This is the first module of chapter 4. The chapter 4 is devoted to find a root of a nonlinear equation or a system of nonlinear equations. A nonlinear equation is either an algebraic equation or a transcendental equation. In algebraic equation, each term is a product of a constant and x to the power n, where n is a rational number and x is a variable. Whereas in transcendental equation, at least one term must be either a trigonometry function or a logarithm function or an exponential function. Many methods are available to find a root of a nonlinear equations or a system of nonlinear equations, such as bisection method, fixed point iteration method, regular falsi method, secant method, Newton-Raphson method, and many more. Among them, Newton-Raphson methods are widely used due to the rate of convergence of this method is quadratic. Now we consider Newton-Raphson method to find a root of a nonlinear equation. Now we describe Newton-Raphson method to find a root of an algebraic equation or a transcendental equation. This method is also known as Newton's method. Let fx equal to 0 be an equation. It may be an algebraic equation or it may be an transcendental equation. Let x0 be the initial guess, that is the initial approximate root of the equation fx equal to 0. Note that the Newton-Raphson method is an iteration method. So, every iteration method should start with an initial guess or initial root. So, for this case or for this reason, we assume that x0 be the initial guess of the root. Suppose x1 equal to x0 plus h be the exact root of the equation fx equal to 0, where h is the correction or called the error occurs in the root x0. That means, if x0 is the approximate root and h is the correction of the root, then x0 plus h gives the exact root of the equation. Therefore, f of x1 equal to 0, or we can write f of x1 equal to f of x0 plus h equal to 0, and by Taylor series expansion this becomes f of x0 plus h into f dash x0 plus h square by factorial 2 into second derivative of f at x0 plus dot 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 equal to 0. Since h in general, h is a small quantity, therefore we can neglect the square and higher power terms of h, and after neglecting these terms we get f of x0 plus h f of f dash at x0, f dash means the first derivative of f, equal to 0, or h equal to minus f of x0 by first derivative of f at x0. So, this is the correction of errors, that means this is the expression for the error terms h. Note that the value of h is approximate value, not the exact value. Therefore, the value of x1, that means the first approximated value of x, which is x1, and it is equal to x0 plus h equal to x0 minus f of x0 divided by derivative of f at x0. So, this is the first approximate value of the root of the equation fx equal to 0. Now, the second approximation or second approximate root is obtained by replacing x0 by x1 in the first equation. That means, x2 equal to x1 minus f of x1 by derivative of f at x1. This is the second approximate root, and in general the n plus 1 iterated value or n plus 1 approximate root of the equation is given by xn plus 1 equal to xn minus f of xn divided by derivative of f at xn. So, this is the final expression or the final approximate expression to find the root of the equation fx equal to 0 by Newton-Raphson method. The above formula generates a sequence of numbers x1, x2, dot dot dot, xn, dot 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 dot, and if this sequence converges to a number, then that number is the exact root of the equation. That means the terms of this sequence go to the exact root xi, and the method will terminate when two consecutive values of the approximate root, that means xn plus 1 and xn, and their difference is very small. That means absolute value of xn plus 1 minus xn is less than epsilon, where epsilon is a pre-assigned very small positive number called the error tolerance. This method, that means the Newton-Raphson method that one described in earlier slide, may be used to find a complex root of the equation f(x) equal to 0, but in this case the initial root must be taken as a complex number instead of a real number. This is the geometrical interpretation of Newton-Raphson method. Note that the method is started from the initial guess x0, and we draw a tangent at the point A whose coordinate is x0 f of x0, and that tangent cuts the x-axis at the point x1, and then we again draw a tangent from the point B. The coordinate of the point B is x1 f of x1, and that tangent is cut the x-axis at the point x2, and then we draw another tangent at the point C, and gradually the tangent generates a sequence of numbers, and that number goes to the exact root xi, and xi is the exact root, and which is the intersection of the curve and the x-axis. So lot of tangents are drawn in Newton-Raphson method. So for this reason this method is also known as method of tangents. But the choice of initial guess of Newton-Raphson method is a very serious task. If the initial guess is close to the root, then the method converges rapidly, but if the initial guess is not much close to the root, or if it is wrong guess, then the method may generate an endless cycle. Also, if the initial guess is not close to the exact root, the method may generate a divergence sequence of approximate root, that means sequence of number diverges. Thus, to choose the initial guess, the following rules is suggested. So in this rule we assume that a root of the equation f(x) equal to 0 be in the interval closed interval ab, and if fa into second derivative of f at x is strictly greater than 0, then x0 equal to a may be taken as the initial guess of the root, and if fb into second derivative of f at x strictly greater than 0, then x0 equal to b may be taken as the initial guess of the root. So these are the rules to choose the initial guess of Newton-Raphson method. The Newton-Raphson method is not applicable for all types of function. For example, if the first derivative of f at xn is 0 or very small, then the method fails. Now we discuss the condition for convergence of Newton-Raphson method. The condition is if the absolute value of the derivative of the expression x minus f(x) by first derivative of f at x is less than 1, or absolute value of f(x) into second derivative of f at x is strictly less than absolute value of first derivative of x power 2. If this condition is satisfied, then the Newton-Raphson method converges. Also, the Newton-Raphson method converges if the initial guess x0 is chosen sufficiently close to the root, and the function f(x), first derivative of f and second derivative of f are continuous, satisfy the above condition 3 and bounded within the interval ab, then this method sure converges to a root. This is the sufficient condition for convergence of the Newton-Raphson method. If this condition is not satisfied, then the method may also gives an approximate root, and which is approximate to the exact root xi. Now we shall discuss about the rate of convergence of Newton-Raphson method. We will prove that the rate of convergence of Newton-Raphson method is quadratic. The Newton-Raphson iteration scheme is xn plus 1 equal to xn minus f of xn by first derivative of f at xn. Let xi be the exact root of the equation fx equal to 0 and xn be the nth approximate root of the same equation, and epsilon n be the errors occurs at the nth iteration, that means xn equal to epsilon n plus xi, and since xi is an exact root of the equation, therefore fxi equal to 0. Now from equation 4 we have epsilon n plus 1 plus xi, this is the value of xn plus 1, equal to epsilon n plus xi, this is the value of xn, minus f of epsilon n plus xi by derivative of f at epsilon n plus xi. Now after simplification, the last equation reduces to this form: epsilon n plus 1 equal to epsilon n minus f xi plus epsilon n f prime xi plus epsilon n square by 2 f double prime xi and dot dot dot. This is obtained by expanding f of xi plus epsilon n by Taylor series method, and similarly we obtain the infinite series by Taylor series expansion from the denominator. Since the value of f xi is 0, therefore we can take common out f prime xi from numerator and denominator. Therefore the expression is reduces to this form, and which is equal to epsilon xi minus the first expression of second term is the numerator and second term is the denominator, and after expanding the second term and after simplification we get epsilon n plus 1 equal to half of epsilon n square into second derivative of f at xi by first derivative of f at xi plus order of epsilon n cube. Since epsilon n is a very small number, therefore we can neglect the terms epsilon n cube and higher power of epsilon n. Then the error expression becomes epsilon n plus 1 equal to c into epsilon n power 2, where c equal to second derivative of f at xi divided by 2 into first derivative of f at xi, and this is a constant because this term is free from the error term epsilon n. Note that this expression is a quadratic expression of the error term epsilon n. Therefore, the rate of convergence of Newton-Raphson method is quadratic. Now we consider an example to illustrate the Newton-Raphson method to find a root of the equation x cube minus 2x 2 into sin x minus 2 equal to 0, correct up to 5 decimal places. Note that this is a transcendental equation. Let fx equal to the given equation, that means the function f x cube minus 2 into sin x minus 2, and we see that, or it can be easily verified that one root lies between 1 and 2. So we let the initial guess x0 equal to 1, and the iteration scheme is xn plus 1 equal to xn minus f of xn by f prime xn, and after substituting the values of f of xn and f prime xn, we obtain the last equation or last expression. The sequence of xn for different values of n are shown in the following table. The first column represents the iteration number, second column represents the value of xn, that means the value of approximate root at n iteration, and last column represents the value of x at the n plus 1 iteration. Note that after 5 iteration we obtain a root which is correct up to 5 decimal places, and the root is 1.58736. So this is a root of the given equation, and this root is correct up to 5 decimal places, and the number of iterations taken by the method is 5. Now we consider another type of example. The problem is find an iteration scheme to find the kth root of a number a, where a is any real number or it may be a complex number, and hence find the cube root of 2. So for this purpose we assume that the kth root of the number a is x, that means we can write x to the power k minus a equal to 0, and let x to the power k minus a be the function fx, and for this function the Newton-Raphson iteration scheme is this one, and after substituting the value of f and f derivative we obtain finally k into xn power k minus xn power k plus a whole divided by k into xn power k minus 1, or it can be written as 1 by k whole into k minus 1 into xn plus a by xn power k minus 1. So, this is the iteration scheme to find the kth root of any number a. Now, for the second part, we have a equal to 2 and k equal to 3. So, for this problem, the iteration scheme reduces to xn plus 1 equal to 2 by 3 into xn power 3 plus 1 by xn power 2. Now, all the calculations are shown in the following table. In this case, we have assumed that the initial guess x0 equal to 1. After third iteration, we get the value of xn, and that means the final value of cube root of 2 is 1.2599, and this value is correct up to 4 decimal places. Note that only 3 iterations are required to get this value. So, using this formula, we can find the cube root or any other kind of root of any number. Now, we consider another example. Suppose 2 into xn plus 1 equal to 5 into xn power 3 plus 1 by 9 is an iteration scheme obtained by any method. It may be Newton-Raphson method or any other iteration methods. To find the root of the equation fx equal to 0, our problem is to find the function fx. Let L be a root obtained from this iteration scheme, the given iteration scheme. Then, as by definition of the root, we can write limit n tends to infinity xn equal to L. Xn is the approximated root, nth approximated root, and L is the exact root. Therefore, from the given iteration scheme, we can write limit n tends to infinity of 18 into x n plus 1 equal to 5 into limit n tends to infinity xn power 3 plus 1, or it can be reduces to 18 into L equal to 5 into L cube plus 1, or after simplification it is 5 L cube minus 18 L plus 1 equal to 0. Therefore, the required equation is 5 into x cube minus 18x plus 1 equal to 0. That means the function fx is equal to 5x square minus 18x plus 1. Now, we consider another example to illustrate the Newton-Raphson method to find the root of the equation, a special kind of equation. The equation is of the form x to the power 15 minus 1 equal to 0, starting with the initial guess x0 equal to 0.5. This is a very interesting problem, and it is obvious that the real roots of the given equation are plus minus 1. So, we consider fx equal to x to the power 15 minus 1, and its sequence, the Newton-Raphson iteration scheme is xn plus 1 equal to xn minus xn power 15 minus 1 by 15 into x to the power xn to the power 14, and after simplification it becomes 14 xn power 15 plus 1 divided by 15 xn power 14. Let the initial guess be 0.5. Then the first approximated value x1 equal to 1092.7333. Note that the value of x1 is 1092.7333, and it is far away from the exact root 1 or minus 1. So, this initial guess is not acceptable to find the root of this type of equation. But if we consider the initial guess as 0.9, then the first approximated value is x1 equal to 1.131416, and note that this is very close to the exact root 1. So, initial guess of Newton-Raphson method is a very crucial issue, which initial guess gives the convergent iteration scheme, and which initial guess gives the divergent iteration scheme. So, this is a very useful or important issues of Newton-Raphson method. The Newton-Raphson method is described to find a root of a nonlinear equation. We have also proved that the rate of convergence of Newton-Raphson method is 2. but the Newton-Raphson method is not applicable for all kind of functions we have mentioned earlier. After development of Newton-Raphson method, lot of modifications have been made. Two such modifications will be described in this module. The first one is the modified Newton-Raphson method be used to find the multiple root of an equation. The standard Newton-Raphson method may be used to find a multiple root of an equation, but the modified methods gives more first convergence iteration scheme. Now we describe Newton-Raphson method to find multiple root of an equation f x equal to 0. The standard Newton-Raphson method may be used to find all the multiple roots of an equation, but the following modified formula, that means xn plus 1 equal to xn minus k into f of xn divided by derivative of f at xn, where k is the multiplicity of the root. So, this iteration scheme converges faster than the Newton-Raphson iteration scheme. Note that in second term the constant k is multiplied by the expression f of xn by f dash xn. So, this is the modification of the standard Newton-Raphson method. Let xi be a root of the equation f x equal to 0 with multiplicity k. Then, as by definition of multiple root, xi is also a root of the equation f prime x equal to 0 with multiplicity k minus 1. Also, xi is a root of the equation f second derivative x equal to 0 with multiplicity k minus 2. In general, xi is the root of the equation pth derivative of f at x equal to 0 with multiplicity k minus p, where p should be less than k. So, if the equation f x equal to 0 has a root xi with multiplicity k, and if the initial guess is very close to the exact root xi, then the following expressions, that means x0 minus k into f of x0 by f prime x0, x0 minus k minus 1 into f prime x0 by f double prime x0, x0 minus k minus 2 into f double prime x0 by f triple prime x0 and so on, must have the same value. But the rate of convergence of this formula is also quadratic like the Newton-Raphson method. The proof of the rate of convergence of this scheme is available in the text. Now we consider an example to illustrate the modified Newton-Raphson method to find the multiple root. The equation is x to the power 4 minus x cube minus 3x square plus 5x minus 2 equal to 0, and the equation has a multiple root of multiplicity 3. Let the initial guess be 0.5 and f x equal to the given expression, and the first derivative of f is 4x cube minus 3x square minus 6x plus 5, second derivative is 12x square minus 6, and third derivative is 24x minus 6. Now, the first iterated values for the three formulas, that means x1 equal to x0 minus 3 into f of x0 by f prime x0, which is equal to 1.035714, and the approximate value of x1 obtained by the second formula, that means x0 minus 2, which is nothing but k minus 1 into f prime x0 by f double prime x0. After simplification, it is equal to 1.083333, and the third values x1 equal to x0 minus f double prime x0 by f triple prime x0, this is the third formula, and its value is 1.5. So, note that the first two values are very close and close to 1, and this indicates that the equation may have a double root close to 1. So, consider the first approximate value of the root x1 equal to 1.035714, and using this value the second approximated root, that means x2 equal to x1 minus 3 into f of x1 by f prime x1. This is the first formula to get the second approximate root x2, and which is equal to 1.000139, and the second formula to get the second approximate value x2 is x1 minus 2 into f prime x1 by f double prime x1. After simplification, it is equal to 1.000277, and third formula gives the value of x2 as 1.000812. So in this case, we see that the three values of x2s are very close and close to 1. So the equation has a multiple root near to 1 of multiplicity 3, because three values are close to 1. Let the second approximate root be 1.000139 obtained from the first formula, and now we apply the third iteration. The third iterated values are x3 equal to 1.000000, similarly x3 equal to 1 and x3 equal to 1 using third formula. So all these values are exactly equal to 1. So we conclude that the equation, the given equation, has a multiple root of multiplicity 3 and the root is 1. That means the final conclusion is the one root of the equation is 1, correct up to 6 decimal places with multiplicity 3. Now we present another modification on Newton-Raphson method. In Newton-Raphson method, in each iteration, to find the value of xn plus 1, we have to find the value of f prime at xn for all n equal to 0, 1, 2 and so on. That means in each iteration we have to calculate or we have to evaluate two functions, one is f and other is the first derivative of f at the approximated value xn. So for this reason we have to calculate the derivative and it takes lot of times. So a modification is suggested to reduce the computational effort of the Newton-Raphson method. The following method reduces the computational effort. The iteration scheme is xn plus 1 equal to xn minus f of xn by first derivative of f at xn. Note that the modification is made on the denominator of the second term. The term f prime x0 is replaced by f prime xn of a Newton-Raphson method. In this method, the derivative of f is calculated only one point, that means only at the initial guess x0, and obviously it reduces the computational time at each iteration, but the rate of convergence of this method is reduces to 1 from 2. Now we consider one example to illustrate the modified Newton-Raphson method. The equation is x cube minus 2x square plus 1 equal to 0, and we also determine the roots of the same equation using the standard Newton-Raphson method. Let fx equal to x cube minus 3x square plus 1, and it is easy to verify that one root lies between 0 and 1. So we consider the initial guess as 0.5. Here f prime x equal to 3x square minus 6x, and hence f prime at x0, that means f prime at 0.5 is equal to minus 2.25. Therefore, the modified Newton-Raphson method gives the following iteration scheme: xn plus 1 equal to xn minus f of xn divided by f prime x0, and after simplification this scheme is xn power 3 minus 3 into xn power 2 plus 2.25 into xn plus 1 whole divided by 2.25. Now all the calculations are shown below. After 7th iteration we obtain a root, and the root is 0.6527, correct up to 4 decimal places. That means 5 iterations are required to achieve this root, while the standard Newton-Raphson method gives the following iteration scheme, and after simplification the iteration scheme is 2 into xn power 3 minus 3 into xn power 2 minus 1 whole divided by 3 into xn power 2 minus 6 xn, and all the iterations are shown below starting from the initial guess x0 equal to 0.5. Note that after third iteration we achieve the desired root, that means 0.6527, correct up to 4 decimal place. That means the standard Newton-Raphson method gives the desired root after third iteration, but the modified Newton-Raphson method takes 5 iterations to get the same root. That means we can conclude that the modified Newton-Raphson method needs less number of computation, but it takes more number of iterations than the standard Newton-Raphson method. In this module, we have described Newton-Raphson method to find a root of a nonlinear equation and have proved that the rate of convergence of this method is 2. But the Newton-Raphson method is not applicable for all type of functions. The condition is also proved in the text. The other methods which are used to find a root of a nonlinear equation, such as bisection method, fixed point iteration method, regular falsy method, etc., the rate of convergence of this method is linear. So, for this reason the Newton-Raphson method is better than the other methods. In this context, I would like to mention that another modification of Newton-Raphson method is also available in literature, and the rate of convergence of this new modified Newton-Raphson method is 3, which is higher than the standard Newton-Raphson method.